Assalamualaikum and a very good morning. Today we are going to step in the design process of an antenna. So to begin with, we are going to look at the simplest antenna design, which are the dipole antenna and also Yagi-Uda antenna. Okay, let's start with the simplest, oldest and cheapest wire antenna design, which is also known as infinitesimal dipole. This is when the linear wire length L is less than a lambda, and the radius is also a very small or very thin structure with A is less than a lambda, and the structure is positioned along the z-axis. So this is the structure oriented or positioned along the z-axis. And in practice, the infinitesimal dipole or infinitesimal linear wire is not practical, but it is used to represent a capacitor plate in which it provides the capacitive loading to maintain a linearly uniform current across or along the dipole structure. So in this case, the spatial variation of the current is assumed to be constant, given by this equation: I for the structure along the z-axis equal to the vector A for I naught. So the I naught is constant. Okay, the radiated fields of infinitesimal dipole can be determined by considering the vector potential A and F. And next, we can calculate the electric and magnetic field from the source current J and M. Right, since the source only carries an electric current IE, so therefore the magnetic current and also the potential A can be represented by this equation, in which R is the distance from the observation point to the point anywhere on the source. And the E and H field, the electric field and magnetic field components, can be represented by the following equation, in which it's valid everywhere except on the source itself. So since the dipole antenna is symmetry, okay, so in this case the E field component, E field on the phi component is 0. Okay, for the near field and the far field region, so the K, the E field and H field can be simplified by the equations as shown, depending on the region where the field lies on. So for Kr is less than 1, it is in near field region. K is the Boltzmann's constant. It is equal to 1.38 times 10 to the power of minus 23, and R is the distance. All right, from the source to the point of observation. All right, so the ratio between the E to H phi is equal to the wave impedance. Z omega is wave impedance, which is the ratio between the E theta field to the H phi, and it is more or less equal to the intrinsic impedance. And for free space, the intrinsic impedance is equal to 377 or 120 pi ohms. All right, the field forms a transverse. It means that the E and H field forms a transverse electromagnetic TM wave mode in which the wave impedance, the Z omega, is equal to the intrinsic impedance of the medium. Okay, next, the radiated power, power density and radiation resistance of infinitesimal dipole. So the P, the complex power in radial direction, can be determined by P which is the integration of the product between the E and H across the surface area. And P rad is the radiated power, while in the circle component is the magnetic and electric time average reactive power in radial direction. Right, so P rad can be determined by this equation, and for the time average reactive power in radial direction basically decreases rapidly as the distance increases. And since the antenna radiates its real power through the radiation resistance for the infinitesimal dipole, it is found that the average radiated power P rad can be simplified by using this equation, in which the intrinsic impedance equal to 120 pi for free space medium. But if it is not in free space, so you need to consider the impedance for the medium. Right, so I naught is the constant current, L is the length of the dipole, and lambda is the C over F, depending on the frequency the antenna is designed for. And the RR is the radiation resistance that can be calculated by using this equation. Right, so the RR radiation resistance equal to 80 pi squared multiplied by L divided by lambda squared. Okay, next, the directivity of the infinitesimal dipole is depending on the radiation density, WAV. It is basically the product of E and the real part of the E and H field, and the radiation intensity U dependent on the radiation density multiplied by the distance squared. Alright, and the maximum radiation intensity U is happening when theta is equal to 90 degree. So when you look at the dipole antenna radiation pattern, so the maximum radiation is seen at theta equal to 90 degree. Right, so therefore the maximum radiation intensity is reduced to this equation, the intrinsic impedance divided by 2 multiplied by the product of K I naught L divided by 4 pi squared. And the maximum directivity can be calculated by having the D naught. D naught is the maximum radiation directivity equal to 4 pi U max, the maximum radiation intensity divided by P rad, which is equal to 3 over 2. And the maximum effective aperture AEM can also be calculated, because it depends. You can get it from the maximum directivity D naught, which the equation can be reduced to 3 lambda over 2 divided by 8 pi. In summary, for infinitesimal dipole, the directivity is equal to 3 over 2, which is equal to 1.76 dB, and the radiation intensity is equal to sine squared theta, and the maximum radiation intensity is happening when theta equal to 90 degree or pi over 2, and the radiation resistance can be calculated by 80 pi squared multiplied by L divided by lambda squared, assuming that the medium is free space, or else you need to consider the intrinsic impedance of the medium. Okay, let's look at an example. Determine the radiation resistance of an infinitesimal dipole whose length is L equal to lambda over 50. Alright, so from previous slide, we know that the radiation resistance, the RR, is equal to 80 pi squared multiplied by L over lambda squared. So we assume that it is in free space medium. So in this case, the L is given as lambda over 50. So 80 pi squared multiplied by lambda over 50 divided by lambda squared. So this is equal to 80 pi squared multiplied by 1 over 50 squared. It is equal to 0.316 ohm. Okay, so if we compare the radiation resistance to a practical transmission line characteristic impedance, so usually the practical characteristic impedance of the transmission line is either 50 ohm or 75 ohm. But for the given problems, the radiation resistance is very small. It is only 0.316 ohm. Therefore, we will expect that there will be a large mismatch when this dipole is connected to a normal transmission line. Therefore, it will result to very small efficiency of the overall system. With that, thank you.